9.2 Lesson 4, Series and Convergence. The objectives for today's lesson are: 1. Apply the properties of infinite series to find the sum of a convergent series. So that's one part of the lesson, and objectives 2 and 3 go together for the second part of the lesson. Objective 2, you'll be able to write the partial fraction decomposition of a rational expression. And objective 3, you'll be able to find the sum of a series by Objective 3 is you'll be able to find the sum of a series by first rewriting it in the form of a telescoping series using partial fraction decomposition. So objectives 2 and 3 go together, and we'll get to that, but we will begin with objective 1, using the properties of infinite series to find the sum of a convergent series. So these are the properties of infinite series, Theorem 9.7, and it states the following. If you have a series whose sum is A, and if you have another series whose sum is B, and C is any real number, then the following series converge to the indicated sums. So given that the series here converges to A, if you multiply the nth term of that series by the constant C, then it's like you're multiplying every single term of this series by the constant C. So the sum of the series here in number 1 will be C times the sum of the series that we have in the hypothesis. And numbers 2 and 3, the only difference between them is in number 2, you're adding the two convergent series from the hypothesis. So you're taking the nth term of the first series and adding it to the corresponding nth term of the second series to form a new series. And what this states is that the series that you have here for number 2 will also be convergent, and it will converge to the sum of A and B. And in number 3, you have a difference of two series, and that series will also converge, and it will converge to the difference of A and B. Here is another way we want to look at number 2. Here is another way that we can rewrite property number 2 using what we have in the hypothesis of this theorem. So we have two series that converge, the first one to A and the second one to B. And all we're doing here is we're just adding the nth terms of the two series. So you can rewrite this in this way. This is going to be from n is equal to 1 to infinity of A sub n plus from n is equal to 1 to infinity of B sub n. And of course, when you take two convergent series and you add them, the sum will be A plus B. And that's what property 2 states. And property 3 is similar, except you have a difference. So now we'll take a look at an example. So here is our example. Notice that the index starts at 0, but these properties are applicable regardless of whether the index starts at 1 or 0. And what you can do is you can see that the nth term of the series that we're looking at as our example is a sum. So we're going to use property number 2. And property number 2 allows us to rewrite our series as a sum of two individual series. So now we can write from n is equal to 0 to infinity of 0.7 to the n plus from n is equal to 0 to the infinity of 0 to infinity of 0.9 to the n. So I used property number 2, and this problem is now very simple. All we have to do is determine whether each of these two series will converge, and if they do, we just add their sums together and we'll get the sum of the series that we have here. So each of these series are geometric series, and because the absolute value of the common ratio is between 0 and 1, we know that each geometric series will converge. And furthermore, a convergent geometric series will have the sum a over 1 minus r. And in the first series, a is equal to 1 and r is 0.7. And in the second series, a is equal to 1 and r is 0.9. And as we learned yesterday, the formula is valid when n starts at 0. And if n had started at 1, you would have to adjust by subtracting the term that you're missing from the sum. But we don't have to do that here. So now we have 1 divided by 1 minus 0.7, which is going to be 1 divided by 0.3, plus 1 divided by 1 minus 0.9, which is 1 divided by 0.1. So now we can complete the problem here. So I have 1 divided by 3/10 plus 1 divided by 1/10. So 1 divided by 3/10 is 10 over 3. 1 divided by 1/10 is 10 over 1. So you can write that as 10 over 3 plus, you can multiply here by 3 over 3. So we have a common denominator of 3. So that's going to be 30 over 3. And our sum will be 40 over 3. So this is how we use properties of infinite series to do the problem that we just looked at. Because when you look at the original problem, obviously the nth term here is not of the form a times r to the n. So we cannot directly use what we learned about geometric series. However, we can apply theorem 9.7, rewrite the given series as a sum of two geometric series, and then use what we learned yesterday. So that was objective 1. Now we move on to objective 2 and 3. Objectives 2 and 3. And we're doing partial fraction decomposition. That's our vocabulary for today. And for objective 2, you'll be able to write the partial fraction decomposition of rational expressions. So this is actually a review of something that you learned in pre-calculus. So we'll take a look at the concept by having you do this process in reverse first. And then we will learn how to do partial fraction decomposition. And we will apply it to do objective 3. You'll find the sum of a series by first rewriting it in the form of a telescoping series using partial fraction decomposition. So before we look at partial fraction decomposition, we'd like to look at this problem to understand the concept of partial fraction decomposition. So in this problem, we're adding two rational expressions together. And to add two rational expressions, you need a common denominator, just like you need a common denominator to add two fractions together. So our first rational expression has a denominator of 3 times 3n minus 1, and our second rational expression has a denominator of 3 times 3n plus 2. So the least common denominator would be 3 times 3n minus 1 times 3n plus 2. So we need to get that for each rational expression. So our first rational expression will be multiplied by this form of 1. 1 is the multiplicative identity, so when you multiply a rational expression by 1, you don't change it. And our second rational expression will be multiplied by this form of 1. And the purpose for that is to get our common denominator, our least common denominator. So we have that, and when we have our least common denominator, we can add the two numerators together. So our first rational expression will have a numerator of 3n plus 2 after we multiply 1 times 3n plus 2. And our second rational expression will have a numerator of negative 3n plus 1 after we multiply negative 1 times 3n minus 1. So now we need to add the two numerators together, and when we do that, we get 3n plus negative 3n is 0n, and 2 plus 1 is 3, and our denominator is the LCD. We can cancel the common factor of 3 that's in the numerator and the denominator, leaving us with 1 over 3n minus 1 times 3n plus 2. And if we multiply the two factors and the denominator, if we multiply the two factors in the denominator, our denominator will become 9n squared plus 3n minus 2, and our numerator is 1. So this is called the addition of rational expressions. So we began here and we end over here. What is partial fraction decomposition? Partial fraction decomposition is the reverse of what you just saw. In partial fraction decomposition, you will begin here and you will end here. The question is, how do we do that? So let's take a look. We're going to look at partial fraction decomposition for this rational expression. And the first step, if you look at the process that we did for the addition, what was the last thing that we did? We multiplied these two factors in the denominator. So when we do partial fraction decomposition, the first step is to factor the denominator so that you will have it like what we have here. And then after that, you have to write what we call the form of the partial fraction decomposition, and then you will proceed to solve for the constants in the numerator in the form of the partial fraction decomposition. We'd like to take a look at that process, and this process is called partial fraction decomposition. So we're actually going to combine objectives 2 and 3. In Objective 2, you'll be able to write the partial fraction decomposition of rational expressions, so we're going to look at that. But then we want to combine it with Objective 3. You'll be able to find the sum of a series by first rewriting it in the form of a telescoping series using partial fraction decomposition. And we'll look at number 50 as our example. So here we have number 50. Find the sum of the convergent series, and you'll notice that the description of the nth term is the same as the result of the addition of the two rational expressions that we did earlier. So now we're going to rewrite the nth term using partial fraction decomposition, and the purpose for that is this. When you look at number 50 as it is given right now, you would not think that this is a telescoping series. But it is, in fact, a telescoping series. But to discover that, you have to begin by rewriting the nth term using partial fraction decomposition. So that's what we're going to do. We're going to rewrite the nth term using partial fraction decomposition. When you do that, you will see that what we have here is a telescoping series, and then we're going to do what we did yesterday. We're going to write a formula for the nth partial sum of the telescoping series by using the observed pattern of how different fractions add to 0 and what's remaining. And then we will use the definition of a convergent series, which states that a series converge if its sequence of partial sums converges. So we'll take the limit of the nth partial sum as n approaches infinity to see if the sequence of partial sums converges, and if it does, then the telescoping series will converge. So now we go back to Objective 2. We're going to do some scratch work. We're going to do partial fraction decomposition. So we will begin with some scratch work in which we will do partial fraction decomposition to rewrite the nth term of our infinite series. The first step in doing partial fraction decomposition is to factor the denominator. So we take our denominator of 9n squared plus 3n minus 2, and we factor it so that we have in the denominator 3n minus 1 times 3n plus 2. The second step is to do something called writing the form of the partial fraction decomposition. the form of the partial fraction decomposition depends on how the denominator factors. So we're only going to look at one particular form of the partial fraction decomposition. And the one that we look at today is what happens when your denominator factors as a product of distinct linear factors. Distinct means the factors are not repeating. And linear means that you've got linear factors. So the variable is raised to the first power in each factor. So when you have distinct linear factors for the denominator, you can write the form of the partial fraction decomposition as follows. As I already stated, depending on how the denominator factors, you will have different forms of partial fraction decompositions, but we're only going to focus on this particular case for today. So here is how we write the form of the partial fraction decomposition if our denominator factors as a product of two distinct linear factors. So for each distinct linear factor, you will have one partial fraction. So you will have one partial fraction for the linear factor 3n minus 1, and the denominator of that partial fraction will be 3n minus 1. And you'll have another partial fraction for the linear factor 3n plus 2, and the denominator of that linear factor will be 3n plus 2. The numerator of each linear factor will be constants. And we don't know what the values of those constants are, so we represent them with these variables, uppercase A and uppercase B. And again, the numerators, what they are, also depends on what form of partial fraction decomposition you have. But if you have this form of partial fraction decomposition, where the denominators are linear factors, then the numerators will be constants. And now to complete the partial fraction decomposition, what we have to do is we have to find what A and B should be. What should the values of A and B be? What do A and B have to be so that what we see here that I just boxed in gold will be an identity? And why do we want this to be an identity? Because we're just trying to rewrite 1 over 9n squared plus 3n minus 2. We're just trying to rewrite that in an algebraically equivalent form. So we want the right side to be identical to the left side. We want the two expressions to be identical. So we want the expressions to be equivalent. So we've got to find the values of A and B that will make that so. So the way you actually find the values of A and B that will make this equation an identity is you assume that you have an identity and you work backwards to find A and B. What does it mean to say that we have an identity? It means that the two sides of this equation will be equal to each other for any value of n, because the two sides of the equation are identical expressions. That's what it means for us to have an identity. The two sides of the equation are identical or equivalent expressions, just in different forms. So to find the values of A and B, the constants A and B that will give us an identity, we work backwards. We assume that we have an identity, and we work backwards to find the values of A and B. So in this process, we will begin by multiplying both sides of this equation by the least common denominator. We will now multiply both sides of this equation by the least common denominator. The least common denominator is 3n minus 1 times 3n plus 2. So we do that to both sides of the equation. And when we multiply by the least common denominator on the left side of the equation, you'll see that it will cancel with the denominator, leaving us with 1. And on the right side of the equation, you will distribute the least common denominator to each partial fraction. When you distribute it to the first partial fraction, the 3n minus 1 will cancel with the denominator, leaving a times 3n plus 2. And when you distribute it to the second partial fraction, the 3n plus 2 will cancel with the denominator, leaving you with b times 3n minus 1. We call this the basic equation. And our next step is to solve this basic equation. And how do we solve this basic equation for a and b? Again, we're assuming that we have an identity, so you can substitute any value you would like for n, and the two sides should be equal, because we're assuming that we have an identity and working backwards to find the values of a and b that would make this an identity. So what you want to do is you want to choose a value of n that would make each term equal to 0. So for example, if you choose n to be 1/3, 3 times 1/3 will be 1, and 1 minus 1 will be equal to 0. So I can focus on solving for a by choosing n to be equal to 1/3. So I choose n to be equal to 1/3, and when I do that, this is what we will have. So I will have a, and then 3 times 1/3, 3 times n, plus 2, plus b, times 3 times 1/3 minus 1. 3 times 1/3 is 1. 1 plus 2 is 3. And of course, for the second term, 3 times 1/3 is 1. 1 minus 1 is 0. So I just have 1 is equal to 3a plus 0. So a is equal to 1/3. So we just found what a should be. A should be 1/3, and I'll go ahead and write that here. We'll note that a should be equal to 1/3. So now we will solve for b. And the way we will solve for b is we need to choose a value of n that would make 3n plus 2 equal to 0, so that we will have an equation 1 is equal to b times some number, and we can solve for b. So the question is, what should we make n equal to so that 3n plus 2 will be equal to 0? So n is going to be negative 2/3. You can do that mentally, or if you want, you can set the factor 3n plus 2 equal to 0 and solve for n, and you get 3n is equal to negative 2, so n has to be negative 2/3 to make this factor equal to 0. So we substitute negative 2/3 for n in our basic equation, and when we do that, this is what we have. And 3 times negative 2/3 is negative 2. Negative 2 plus 2 is 0, so we have a times 0, which will be 0, plus b times 3 times negative 2/3 is going to be negative 2. Negative 2 minus 1 is negative 3. So we have 1 is equal to negative 3b, so b is equal to negative 1/3. So now we know both a and b. B is equal to negative 1/3, and a is equal to positive 1/3. So with that, we have actually found the partial fraction decomposition. So to complete our work, we're just going to take the values of a and b that we found, and we will substitute them for a and b in the form of the partial fraction decomposition as I have done here. And one thing that you can do is to simplify each of these partial fractions by dividing the numerator, which is 1/3 here, by 3n minus 1. And in the second partial fraction, you will divide negative 1/3 by 3n plus 2. And when we do that, this is what we get. This is the partial fraction decomposition of the nth term from our infinite series. So now we come back to our original problem, which is right here. The original problem says, find the sum of the convergent series. And what have we done? We used partial fraction decomposition to rewrite the nth term of our infinite series as a difference of two partial fractions. Having done that, you're going to see that what we have here, the nth term is a difference of two fractions, and in fact, this turns out to be a telescoping series. So now you're going to find a formula for the nth partial sum for our telescoping series, and then you will take the limit of the nth partial sum as n approaches infinity, and if that limit exists, then the telescoping series converges by the definition of a convergent series. So when we take a look at our objectives, we just achieved objective 2. You'll be able to write the partial fraction decomposition of rational expressions. And why do we do that? So that you can find the sum of a series by first rewriting it in the form of a telescoping series using partial fraction decomposition. And of course, we've already done work with telescoping series yesterday. So the rest of this lesson is just doing the same thing that we did yesterday. We're going to take our series that we rewrote using partial fraction decomposition. We're going to look for a pattern in the partial sums, write a formula for the nth partial sum, and take the limit of the nth partial sum as n approaches infinity. And if that limit exists, the sequence of partial sums converges, and therefore, by definition, the infinite series will converge to the same sum. So we will conclude our lesson by doing that. So now we will conclude our lesson by looking at objective 3. You'll find the sum of a series by first rewriting it in the form of a telescoping series using partial fraction decomposition. And of course, we did objective 2, so we're able to rewrite our original problem in the way that we saw. And we will use that to continue with objective 3. So number 50 can be rewritten like this using partial fraction decomposition. And we can further rewrite this because if you look at the two partial fractions, you'll see that each of them has a common factor of 1/3. So we can factor out 1/3 from each partial fraction and rewrite the problem as follows. And from a series, if you have a constant factor in the nth term, you can factor it out of the summation. Our objective now is to see if we can write a formula for the nth partial sum of our telescoping series. So we would like to see if there is a pattern and then use that pattern to write a formula for the nth partial sum. To see our pattern, we'd like to write the first, the second, the third, the fourth, and maybe the fifth partial sums to see what's going on as far as the telescoping effect goes. Which fractions are adding to 0 and what is remaining. To help us write the first, second, third, fourth, and fifth partial sums, we begin by writing what the first, second, third, fourth, and fifth terms of the series are. The first partial sum would be just the first term of the series. And for the second partial sum, we're going to go ahead and add the first two terms of the series. And if you add the first two terms of the series, then negative 1/5 and the 1/5 will add to give you 0. So the second partial sum would be 1/2 minus 1/8. The third partial sum, the negative 1/8 and the positive 1/8 will add to give you 0, and you'll have 1/2 minus 1/11. The fourth partial sum, when you add the first four terms, what we've already circled in blue will add to give us 0. and negative 1/11 and 1/11 will also add to give us 0. So we'll have 1/2 minus 1/14. And the fifth partial sum, again, everything that we've already circled in blue will add to give us 0. And also negative 1/14 and positive 1/14 will add to give us 0. So we'll have 1/2 minus 1/17. So we find a pattern, and we can use that to help us write the nth partial sum. So the nth partial sum, as you can see from the first 5 partial sums, we will always have 1/2. So we will have 1/2, and then all the other fractions in the middle will add to 0, but you are left with subtracting the second fraction of the nth term. So for example, in the fifth partial sum, we subtracted the second fraction of the fifth term. So in the nth partial sum, from 1/2, we will subtract the second fraction of the nth term, which is, of course, 1/3n plus 2. So we have 1/2 minus 1/3n plus 2. So that's our formula for the nth partial sum, and we can use that to determine whether our series here that I'm boxing in gold will converge. By the definition of a convergent series, if the sequence of partial sums converges, then the series converges. So how do we determine that the sequence of partial sums converges? We take the limit of the nth partial sum as n approaches infinity, and of course when you do that here, that limit will be 1/2. So our sequence of partial sums will converge to 1/2, and therefore by definition our telescoping series will converge to 1/2. So we know that our telescoping series will converge to 1/2 by the definition of convergent series, because its sequence of partial sums will converge to 1/2, therefore the series will converge to 1/2. And don't forget the 1/3 that we factored out earlier, so the final answer for our problem would be 1/3 times 1/2, which is 1/6. 1/6 is the sum of our convergent telescoping series. So this is how the series was originally written, and we did this work so that we may determine that the infinite sum that we have here is equal to 1/6. The series converges to 1/6. In the second part of our lesson today, we were able to use partial fraction decomposition of rational expressions to rewrite a given series so that we were able to recognize it as a telescoping series and then find the sum of that telescoping series by examining the limit of the nth partial sum as n approaches infinity.